Hi everyone, welcome to today's class. I'm happy you are there. Please join us, let us do justice to this topic, capacitors. Now, the question we ask ourselves is, what is a capacitor? A capacitor is nothing but a device for storing electrical charges. Now, of course, it is indirect current that capacitors store charge. But in alternating current, capacitors do not store charges in AC circuit. In AC circuit, they oppose charges or the flow of current. Now, let us see this capacitor. Now, this capacitor in the direct current also, capacitors store charge, and they are made of two equal but opposite charges. So this is if this is a capacitor, now these are plates. So is plates of two equal but opposite charges. Okay, since it is equal but opposite charges, that means just by equal, one is positive, one is negative, separated by a distance, d. So this is a capacitor down here, but it is separated by a distance d. Now this distance here, so we have this is a metal plate, both these and these are metal plates. Now, this is a distance, that distance is just a gap there. It's an insulator. An insulator is placed between these plates. So it's an insulator called dielectric substance, or dielectric constant. Okay, why here is V? The potential difference. If you look at these two, the polarity are not the same, but for this one they are the same. So they are carrying equal but opposite charges. So capacitors can come in different shape and sizes. There are metal ones, and there are some that come in paper form. Okay, so of course they are found in our electrical gadgets, electrical devices, even our generator sets. So they are found there. Okay, so we now look at this dielectric substance, which is this distance here. So we say that a dielectric substance is nothing but an insulator placed between two plates of a capacitor. So that is what a dielectric substance is. So it's just an insulator. So if you remove this from here, it has its own role it will play. Okay. So we now have that. After that, we now look at capacitance of capacitor. Capacitance of a capacitor. C. Capacitance of a capacitor C. Now, this capacitance of a capacitor is nothing but the ability of a capacitor to store up charges. The ability of a capacitor to store up charges is known as capacitance of a capacitor. It can also be expressed as the ratio of charge to potential difference. So we say that capacitance of a capacitor is a ratio of charge to the potential difference between the plates. Okay, having said that, we can now discuss the factors that affect the capacitance of a capacitor. Factors that affect the capacitance of a capacitor. Now, there are basically three factors that affect the capacitance of a capacitor. The first one is, of course, you can feel the thickness. So when I say thickness or area of plates, area of plates affects it too. And of course, you know, the thicker the plate, the more the capacitance. Now, we have the second one. We have a dielectric substance. Dielectric substance, or nature of dielectric substance, which is this substance here. Now, the third one is distance between plates. Distance between plates. Distance between plates. Let me write it in full. Between plates. So these three majorly are the factors that affect the capacitance of a capacitor. Most times in exams, you might be asked to state the factors that affect the capacitance of a capacitor and how they affect these capacitor or the capacitance of the capacitor. How they affect the capacitance of the capacitor. So in other words, to answer that question, I will advise you to answer it in a tabular form. So we can put up factors here, and then we put the effect on this side. So the first factor, just like we said, area of plates. So what is the effect on the capacitance of the capacitor? You can now say that increase in area increases the capacitance of the capacitor. That is the first one. Increase in area increases the capacitance of the capacitor. Now, in next one, you can say nature of dielectric substance. Nature of dielectric substance. You can now say that yes, the nature of dielectric substance has effect on the, so increase in dielectric substance increases the capacitance of the capacitor. Number 3, which is distance between plates. Distance between plates. How does it affect the capacitance of the capacitor? Now, if you keep these two plates wide, it will reduce the capacitance of the capacitor. If you bring it closer, it will increase the rate of storage of this capacitor. In other words, we can now say that yes, increase in distance between plates decreases the capacitance, of capacitor. Capacitance of the capacitor. Okay. So if you answer it like this, I assure you, you will get the full mark. Now we now look at how these factors can affect this. Remember, this is area between plates. Dielectric substance is expressed as the permittivity of the free space, and distance is expressed as small letter t. So when I put the 3 together, if we put the 3 together, it will give us an equation that will help us solve the problem of the capacitor. So we now say that yes, the capacitance of the capacitor can now be expressed as epsilon 0a all over G, where this is permittivity of free space. It is a constant anyway. The value is 8.85 times 10 to the power minus 12 farad per meter. Sorry, I forgot to tell you that the SI unit of capacitance of the capacitor here, the SI unit, remember, this is in coulomb, while this one is in volts. Therefore, the SI unit of capacitance is coulomb per volt, or otherwise known as farad, designated with letter F. So, that is why we now have this as farad per meter. farad per meter, please. Okay. Now we have two equations for calculating capacitance of the capacitor. So let us take one or two calculations to buttress our information. Now the first question we'll ask ourselves is this. The charge on either plate of a 3 microfarad capacitor, the charge on each plate of a 3 microfarad capacitor, 3 microfarad capacitor, is, that is the charge now, is 6 times 10 raised to the power minus 6 coulomb. Calculate the PD between the plates. Calculate the PD between the plates. Now all we need to do is, remember, this is micro. Micro means, so with this now, micro means 10 raised to the power minus 6. So anytime you see micro, please make sure you take care of it, which is 3 times 10 raised to the power minus 6 farad. That is our capacitor now. So we have this. So we now have that. Using that formula, we make V the subject. If we make V the subject, V will now give us Q all over C, and which will give us Q is 6 times 10 raised to the power minus 6 all over 3 times 10 raised to the power minus 6. And then this one can take care of this. 3 can cancel 2 to give us 3 can cancel 6 to give us 2. Therefore, V is 2 volts. That is the potential difference between the plates is 2 volts. Now we'll take another question, and this one says a capacitor of charge 7 times 10 raised to the power minus 6 coulomb. 7 times 10 raised to the power minus 6 coulomb has a PD, has a potential difference. So C is 7 times 10 raised to the power minus 6 coulomb, has a potential difference of 110 volts. What is the capacitance of the capacitor? What is the capacitance of the capacitor? So we now have that C is Q over V, which will now give us, okay, sorry, this is a Q, please. So which will now give us 7 times 10 raised to the power minus 6 all over 110, which will now give us, this, if you count 7 divided by 1, so we have 7 over 110 will give us 0.064 times 10 raised to the power minus 6. Therefore, C, capacitance of the capacitor, will give us 6.4 times 10 raised to the power. Now, if you move this, it will increase by 1. Move it again, it will increase. It will now have minus 8 farad. So this is the capacitance of the capacitor. Now we take the next question, and this question says a parallel plate capacitor of area 10 cm squared, area 10 cm squared, in vacuum has a capacitance of 10 raised to the power minus 2 microfarad. What is the distance between the plates? What is the distance between the plates? I was given that epsilon 0 is 9 times 10 to the power minus 12 farad per meter. Now, the first question we'll ask ourselves, we are looking for the distance, that is what we are looking for. Now, the first question we'll ask is, which formula will satisfy A, C, D, and D? So of course, the only one that satisfies is the one that says C is equal to epsilon 0A all over D. But before we substitute, we check the SI units and then do the necessary conversions. While doing the conversions, we have that, take note of this because I want to clean it. We have that the first thing is area is measured in cm in meter square and not cm square. This one already is in microfarad. So because of that, we'll take this to the appropriate SI unit, which will now give us 10 all over 100. And if we divide it by 100, we have just taken care of cm only. What of this square? Because of the presence of this square, we square this 100. So which will now give us 10 over 100 squared. 100 squared is 10,000, which will give us 10 all over 10,000 will give us 1 times 10 to the power minus 3. 1 times 10 to the power minus 3 squared. And of course, this one, if this one cancels this, we now have 1, 2, 3. So 10 to the power minus 3, we're corrected. This one also, C is minus 10 raised to the power minus 2. Because of this micro, we now have 10 raised to the power minus 2 times 10 raised to the power minus 6 farad, which will give us 10 raised to the power minus 8 farad. So take note of these two. Now we move. We now have, if we employ our formula and then do the necessary conversions, after that we make D the subject. D will give us epsilon 0A all over C, and it will give us epsilon 0, just like we gave earlier, 9 times 10 to the power minus 12 times area. Area is 1 times 10 to the power minus 3 all over C. C, instead of this, we use the converted value, which is times 10 raised to the power minus 8. Now, which will now give us 9 times 1, multiply all the bases. 9 times 1, which will give us 9. 9 times 1 times 10 raised to the power minus 12. This one is already there, minus 3. Now, this one, because this is an index number, you can take it up. If you take it up, once it crosses, the sign changes to plus, it becomes plus 8, which will now give us D is equal to 9 times 10 raised to the power minus 12 minus 3 plus 8 will give us minus 7 meters. So that is the distance between the plates of that capacitor. Now, we take this one. Maybe I will drop this one. Please drop the answer in the comment section. And this one says, a 2 farad capacitor is desired. A 2 farad capacitor is desired. What should the area of the plates be if they are to be separated by 4.4 millimeter air gap? If they are to be separated by a 4.4 millimeter air gap. Given that the permittivity of free space is 8.85 times 10 to the power minus 12 farad per meter. So please drop the answer in the comment section. Let us look at the arrangement of capacitors, how capacitors are arranged. Now, look at this. Arrangement of capacitors. Capacitors can be arranged either in series or in parallel. Now, if it is arranged in series, there are certain things we need to do. There are certain parameters we need to take into place. Now, we have the series and the parallel arrangement. Now, we have, if we have an arrangement like this, we have this. Of course, this is our V. V is here. We have C1, C2, and C3. Maybe we can have this. And of course, this is the flow of charge. Now, there are two things I want us to note here. Total capacitance. Total capacitance or the effective capacitance in series. So, sorry, this is the first one. Capacitors in series. So, this is series connection. So, total capacitance in series is equal to 1 over C. You can say C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now, when capacitors are arranged in series like this, we have that all the capacitors have the same charge. So if you arrange it like this, the same charge flows. But the V here, which is the potential difference varies. So potential difference is highly dependent on the values of these capacitors. For example, if this one is 2 microfarad, this one is 3 microfarad, this one is 4 microfarad, you know, the same charge will flow there, but different potential difference they will gain. So that is why we now say that yes, when they are arranged in series, same charge flows, but different potential difference. Therefore, we now say that voltage is better among the capacitors. So because voltage is better among the capacitors, we now have that voltage is inversely proportional to C. So this is the total capacitor. Now the value of voltage we have is V, inversely proportional to the quantity of capacitor there. Now the second one is capacitors in parallel. Capacitors in parallel. And when capacitors are arranged in parallel, I will also clean this. If I clean this, I will now have the next one is capacitors in parallel. Parallel. Now, when capacitors are arranged in parallel, we can have an arrangement like this. If we have an arrangement like this, we have this, and this. Maybe, let's say, we have this, and this is our potential difference, V. If this is our V, this is, let's say, C1 here, C2 here, and this one is C3. Now, total capacitor is equal to C. You can say C total is equal to C1 plus C2 plus C3. Now, another point I want us to note here is that yes, the former one charge was the same, but for this one, for parallel plate capacitor, when they are arranged, when they are connected like that, we now say that the V that flows is the same, but Q varies. So we now say they have the same potential difference, but Q varies. So in other words, we can now have that if we have this, Q varies directly with the capacitor. Q varies with capacitor because Q varies while the potential difference V is the same. Now let us take one or two calculations Okay, so we now have from this, we have figure 1 and we have figure 2. We will solve them one by one. So we'll solve this one first. Now this one says the figure above, from the figure above, calculate the value of the resultant capacitance and the total charge and the combination. And the total charge and the combination. So there are 2 questions they asked us here. Now the first question is the total, is the capacitance, the total capacitor. So total capacitor. While the second question is the total charge. So we'll now look at this. Now, the first question we'll ask ourselves here is, what kind of circuit is this? If you look at this network, you know that this is, these are just 2 and 4 are in parallel, whereas these and these are in series. So we have a circuit of this nature. All you need to do is first resolve the one in parallel, and the answer you get will now be in series with this. So let's go. Now the first thing we do now is for parallel combination. For parallel combination, we have. So how do we resolve the parallel? Now we now have that C is equal to C1 plus C2, which will now give us that C1 plus C2 is 4 plus 2, which will now give us 6 microfarad. This 6 microfarad will now be in series with this. So we now have total capacitors in series. We now have these 2 and this one put together. We now have 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3, which will give us 1 over C equals 1 over C1. We can take 3 plus these 2 put together, which is 6. 1 over 6 plus 1 over 5, which will now give us that 1 over C equals LCM of 3, 6, 5 will give us 30. 3 divided 30, 10. 10 times 1, 10 plus 6 into 30, 5 plus 5 into 30 will give us 6, which will now give us 21 over 30. Therefore, remember this is inverse. Inverse means C. So, in order to get C, you turn this. Turning this means 30 over 20. 30 over 21, which will give us 30 divided by 21 will give us 1 point. Therefore, C is 1.43 microfarad. So this is the total capacitor in this circuit. Now for the second question that says total charge, please permit me. I'll write somewhere here. For the total charge, okay, let me write it here. For the total charge, Q is equal to CV. Now, charge will now give us, C is 1.43 microfarad, remember it's micro, times V. V is 500. Now we now have 500. Everything will now give us 1714.3 microcoulombs, because this is a C, microcoulombs. Or we can have 714.3 times 10 raised to the power minus, remember this is minus 6 coulomb, which will now give us 7.143 times 10 raised to the power minus 1, 1, 2 minus 4 coulomb. That is the answer. So the total charge flowing in this network is 7.143 10 to the power minus 4 coulomb. Or if it is a micro, this is what you now have. Now we want to solve this second question. The second question says, calculate the capacitance of the capacitor in the circuit above. Meanwhile, if we clean this, we can solve that problem. The same question we ask ourselves, what is the nature of network we have here? Now from here, you now notice that there's a junction here. These are just straight lines. We can say P, Q. These are two lines, line P and line Q. Now, we have this connected in between. So, 1, 2, 3 are in parallel. The only one that are in series, just these two are in series on this line. What we do is we resolve the one in parallel first, and then they will now be in series with this. So, we now have the first one, total capacitance in parallel. Total capacitance in parallel will give us C equals C1 plus C2 plus C3, which will now give us 2 plus 2 plus 2 plus 2, give us 2 plus 2 plus 2, will give us 6 microfarads. Now, having gotten this, these ones put together will now be in series with this. So we now take the second one. Total capacitance in series. Total capacitance in series will give us 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3, which will now give us 1 over C equals 1 over, the first one here, you can say 1 over 2 plus the second one, 1 over 3 plus combination of this one, which is 6, 1 over 6, which will now give us 1 over C is equal to LCM of 6, 3 and 2 is 6. Now 2 into 6 is 3. 3 times 1 is 3 plus this into this is 2 plus 6 into 6 is 1. So which will now give us, if you add this up, you now have 6 over 6 and 6 over 6 is 1. Therefore, total capacitor in the series, total capacitance in the circuit is 1 microfarad. And this is our answer. Okay, the last but not the least, we will take another one. Now we have the installed top question here. In the network shown, determine the potential difference across the 5 microfarad capacitor. And of course, this is a recent JAMB question. We have options 3, 6, 12, and 18 votes given to us. Here we have the PD flowing here, and of course, if you look at this combination, we have this is a combination of both series and parallel. Now, the question says the PD across the 5 ohm. All you need to do, this 5 ohm is in series. You forget about this one because you were not demanded to get the entire capacitance in the circuit. So all we need to do is we now see total capacitance in series. Total capacitance in series. Of course, these two are the only one in series. This one is in parallel. We now have that the series connection is 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3, as the case may be, which will now give us that 1 over C is equal to 1 over 5 5 plus 1 over 15. And of course, the LCM of 5 and 15 is 15, which will now give us that 1 over C is equal to 15. 5 into 15 is 3, plus 15 into 15 is 1, which will give us 4 over 15. Therefore, if you make C the subject inverse, so C means invert this other side, which will now give us 15 over 4. Instead of cross multiplying, invert, turn it upside down. And you will now have 4 divided 15, or 15 divided by 4, will give us 3.75. Therefore, C is 3.75 microfarad. This is the one in parallel. And because of that, we can now say that yes, we can calculate the charge. So we now say charge Q, charge flowing in the series connection. Charge flowing in series connection. Remember, from our definition, we said that here, the same quantity of charge will flow when we have series. So, because this one is a series, and our interest is to get the PD here. Okay, V is given. Let us define C. From C, let us find Q. You find our Q, we can now go ahead to get our V. So we now have Q is equal to CV. Quantity of charge that will flow into this. So which will give us C is 3.75 times V. V is 24, which will give us times 24 will give us 90 microcoulomb. This is microcoulomb. So we now say that yes, that Q, the same quantity of charge flowing is 90 microcoulomb. And the same quantity of charge flowing into this one will flow in the two because they are in series. Therefore, we can now calculate our potential difference across. Therefore, PD across the 5 microfarad capacitor is V. V5 is equal to Q all over C, which will now give us quantity of charge is 90 microcoulomb all over the charge, the C, the 5 microfarad capacitor. Microfarad. Micro can take care of micro, and then 5 can cancel 9, and then 90 divided by 5 will give us 18. Therefore, potential difference across the 5 microfarad capacitor is 18 volts. And of course, it's option D. Okay, there are so many questions. Please feel free to contact me should you have any other question to solve on this. There are so many questions. Every year, they continue to ask complicating questions. If they don't ask it in WAEC, they will ask it in JAMB. This is where we'll stop. If you find this lesson interesting, please give it a thumbs up. Tell me in the comment section. Don't forget, I gave you a problem earlier. I need to get the answer in the comment section.